When you make a sound, you're actually pushing air particles back and forth. If you look at one specific spot, variation in pressure can actually be plotted. A note like A440 has a pressure wave with 440 iterations occurring each second, while a lower note, C262, only cycles 262 times per second. Combine these two together, and you have a noise that's something like this. For this example, that's essentially the first half of the Fourier transform. Given several frequencies of notes, you can determine the pressure, say, as a function of time, of the final combined noise. The second part of the transform states that the reverse is also true. Given the pressure versus time graph of the combined noise, we can find the frequencies that make up the sound, sort of like unmixing a smoothie to find out the ingredients inside. How is this even possible, you may ask? Well, imagine if you had a series of filters. By passing the smoothie through these, you would be able to tell what the ingredients were. Similarly, you could take the final sound and perform a graphical analysis to determine the pure notes that make up that noise. Let's take the sound wave of a pure note with frequency of 4 Hz. Because this wave could go on forever, let's take a 2-second segment and wrap this around a circle. Right now, the wave is wrapping around twice per second. The unit for cycles per second is Hz. It is important to note that this frequency is different from the frequency of the sound wave itself. The 4 Hz of the sound wave is fixed, whereas the 2 Hz at which the signal is wrapped around in a circle will be changed. Now let's imagine the signal has some mass. The center of mass would move as we change the number of times we wrap the signal around the circle. If we graph the horizontal component of the center of mass, we'll see some interesting behavior when we approach the frequency of the sound signal. It's a spike. So, if we did the same process on nearly any other waveform, we would be able to find out the pure frequencies that create it. Now that we have a qualitative understanding of the phenomenon, let's take a look at the math. Normally, we would label the axes x and y, but the math works out very nicely if we use imaginary numbers for the vertical axis and real numbers for the horizontal. To denote a point, we would use the sum of a real number and an imaginary one. A really cool property of this is that if you have e to the power of some number multiplied by I, it would be the same as if you traveled that distance along the circumference of a circle of radius 1. If we were to go around the circle once per second, e to the power of 2 pi times I times t would give us the equation of the motion. Since we're traveling 2 pi radians, or 1 full rotation, 1 t is equal to 1. However, we don't always go around the circle once per second. We need to add a frequency term, because if the frequency says that the signal goes around the circle once every 3 seconds, by having f as 1/3, the graph will have completed a full circle when t is 3 seconds. Let's call the original waveform w of t. We can use this as a scaling factor, so that as we go around in a circle, we essentially get the wrapped waveform from before. To find the center of mass, we'll need to sum up the locations of all the points and divide this by the number of points. A notation like this does that. This is essentially an average of each point on the graph. In the actual formula, however, they remove the 1 over t2 minus t1. This doesn't change the direction of the center of mass, and it still leads to a spike at the right frequency. It just changes the length of the arrow. The inverse Fourier transform does the reverse, taking the pressure frequency graph and finding the original waveform that produces it. It's the same formula too, just with a negative sign. I'm Richard, and this is the Fourier transform.